So in section 9.2, we're going to be testing claims that involve this null hypothesis. So what kind of a claim is it that we're going to be testing? Well, I guess you can refer to the fact that we've got two of these. So we're testing claims about two population. What does that parameter mu represent?
Mean.
Yeah, two population means. Now, once again, I sent you out a little handout, so we can pull that up, take a look at it, and run through some of the procedures and the assumptions for testing claims about a hypothesis for two population means. And that would be right here. Oops. There it goes. Is that up on your screen here? Hypothesis test for two population means. So we'll look at the assumptions like we normally do at the start of these tests. We got independent samples. Should write simple independent samples. But independence is going to take on a little bit more of a meaning, especially when we do section 9.3. Sigma 1 and sigma 2 are unknown. This makes sense. I don't really realistically see how you would not know the means, yet know the population standard deviation. I just don't see it. There is actually a statistical test that you could do in that circumstance, but I don't see anyone who would ever use it. Both samples are simple random samples. All right, I mentioned that. One of these two are true. So one of the true or both. You have sample sizes that are both greater than 30, or both samples come from a population that is normally distributed. Now, when we did section 8.4 for hypothesis tests regarding a a population variance or population standard deviation, one of the assumptions that was very strict is that you had to have a population that was normally distributed. In this case, if we're not spot on with our assumptions, the test is probably still a good test. It's not as sensitive to departures from the assumptions as our test in 8.4 for population variance and population standard deviation. There, it's a very sensitive test. And in section 9.4, we're going to see even a more sensitive test when we talk about two population variances. For now, a lot of this should start to look familiar, and that is we're going to state the null and alternative hypothesis, decide on alpha, enter the data in Statdisk, and there's instructions there for that. Find the p-value, and then reject or fail to reject, etc. So a lot of this should be the same. I do have one mistake on your handout. The statistic that you're going to use in all this is based on a t distribution. So I accidentally drew a z distribution when I printed up the handout, but that should be a t distribution. Now, the advantage of doing it with some software is that you can actually get a better test, because if you're just doing this kind of old school, like those people who are doing it by hand, then what they're going to say is that the degrees of freedom is small, the smaller of n1 minus 1 or n2 minus 1. So the smaller of those two is going to be your degrees of freedom. But the software is going to give you a better number for degrees of freedom. It's going to do an approximate degrees of freedom, which is going to make your test more powerful. That is, if H naught was false, you have a better chance of rejecting H naught. Okay, let's see here. Let's start with example A. Data on the weight contents of cans of diet soda versus the contents of regular version. Just so you know, we're talking about Coke. I don't know why the software in my math lab has to remove like everything fun, but they're talking about cans of Coke. Assume that the two samples are independent. That's good. Simple random samples, even better. Selected from a normally distributed population. Test the claim that the contents of the cans of diet soda have weights with a mean that is less than the mean for the regular soda. So, all right. Let's see if we can't set up an alternative hypothesis. We're testing claims about means, and we're going to test a claim about the diet soda versus the regular soda in terms of their weights. And which way should I put the inequality or the equal sign? What should go in here for my original claim? Anyone know? Let me take a peek at things this way. There we go. Can you see that? Test the claim that the contents of cans of diet soda have weights with a mean that is less than the mean for regular soda. So what symbol should I put here?
So that like an arrow going towards diet.
Nice, a less than sign. Thank you, Nate. So less than sign, perfect. Now, what's that going to say about, well, is this part of my null or alternative hypothesis? Which one? Amber? Which one's that going to be part of?
I think null.
What has to always be part of the null?
Equal?
Yeah. Is there any equal possibility here?
No.
No. So that has to be part of the alternative. So if this is the alternative, what would be in the null? Anyone?
Greater than or equal to?
Yeah, greater than or equal to. Awesome. Thank you. So greater than or equal to, like this. Now keep in mind that my math lab is probably going to do it this way. They're going to think of it as just equal to. We've discussed it before. This is a little bit more user-friendly, but that's our step one. Step two, what was alpha equal to? Let's see, I think I got to zoom up a little bit. All right, why aren't you cooperating? Yeah, at the 1% significance level. And while we're here, we can copy down some information. I kind of highlighted that in two different colors for diet and regular. So let's get that. So the number of diet cans, call it N sub D, was 30. The mean X bar sub D, remember X bar is going to be your sample mean, not the population mean, 0.783, and that's in pounds. Standard deviation, who was it just a minute ago talking about those three leading zeros? Here they are again. Just coincidence though. 0.00, I guess only two leading zeros, my bad. 0.00447 would be the sample standard deviation. All right, so quick glance at my sheet here. 0.00447. And let's look at the same data for our regular pop. We had 30 cans here. X bar sub R. The average weight in this sample was 0.805 with a standard deviation of 0.00758. So that's the information we need to put into Statdisk. So let's do that. Let's let the software do some work for us. And actually, it's going to do a little bit more work than you might realize. Hopefully, you're getting familiar with where to go. It's analysis, hypothesis testing. What choice are we going to make this time? Marla, which one of these do you think I should select? Proportion one sample, proportion two samples, mean one sample, mean two samples, independent, mean matched pairs, standard deviation, 1 and 2 samples. Anyone?
Mean two samples?
Mean 2 samples, thank you. Another 2 independent samples. We'll start by adjusting our alternative hypothesis. You've got 3 possibilities: the not equal to, the greater than, and the less than, 1, 2, and 3. Which one do we want?
Less than.
Less than, thank you. So less than, let's put that down here at number 3. And then our significance level, need to dial that down a little bit. That's going to be 0.01. Sample size 1 was 30. And the mean there was 0.783. Standard deviation. Where do you think I should enter the standard deviation? Sample standard deviation or population standard deviation? Which one of these do you think I should be using?
Sample.
Sample, yeah. The standard deviation you have there is for a sample. They didn't say, here's the population standard deviation. We don't have that number. We've got the sample standard deviation. So that was 0.00447. What's nice and helpful here is they put if known, which I hope that makes you feel a little bit more comfortable leaving it alone. We don't know that one. So the sample standard deviation goes here. Down here, we've got 30. And then, let's see, what else? 0.805. Sample standard deviation again, 0.00758. So one of the choices you made is by not plugging in the standard deviation, this doesn't turn into a Z statistic. So that's a choice that you made kind of unconsciously. Another choice that you can make is whether or not you think that the variances are equal. And what's that all about? Well, if the variances are equal, you can actually perform a more powerful test, a test that's more likely to find and reject H naught when it's false than it would be otherwise. But chances are you can't make that assumption. Later on, we'll be able to test and see if we can make that assumption. You can use a preliminary F test. But for the most part, I would probably suggest that you do unequal variances. And quite often in the statement of the problem, you'll see something like that. It says, assume that the variances are equal, or assume the standard deviations are not equal. Something like that. So it'll tell you basically if you want to use this one or this one. I think for the most part, they say this one. Those are all the settings. Let's click evaluate. And I'm getting the spiral of death again. I got that all morning in my morning classes. I don't know what's going on with that. But at least I'm getting all the information that I need here. In fact, at this screen here, what is it that I need? What am I looking for? Aiden, what do I need here for step 4?
Wouldn't it be the p-value?
Excellent. And our p-value is what?
Currently, according to that thing, 0.
Yes, it's 0. It's essentially 0 because we got a t statistic that's way, way, way out there. In fact, if you were to plot it, you'd see that it falls way out there in the rejection region. Of course, I'm getting that spiral of death again. So I don't know what's going wrong with this, but you're getting 0. And so thank you, Aiden. That's what we needed. Let's see. Ella, what's that say about our null hypothesis over here in step 5? I've got a p-value of 0 and alpha was 0.01. Do I reject H naught or fail to reject H naught?
Reject.
Yeah, reject. If the p-value is low, H naught must go. And since our p-value is less than alpha, we're going to reject H naught. Yay! So that brings us here into step 6. Step 6, we got to figure out how we're going to word our conclusion. So let's go back to here. And it helps to remember our original claim. So I'll peek back here for a second. The original claim was that cans of diet pop have a mean weight which is less than cans of regular pop. So that's our original claim, aka the orange claim. All right, just kidding on that last part. So our original claim is the alternative hypothesis. Let's see what we're going to do with our decision tree. So I'll erase these things here real quick. Does your original claim contain the condition of equality? What do you think? No. Good. Did we reject the original claim?
Yes.
Yes. So the original claim doesn't contain it, but we rejected it, so that puts you here in C. The sample data support the claim, that, and then you want to state the original claim in words. So let me write that down, and then I'll switch over. The sample data support the claim. That, and now we need to state that original claim in words. So it's going back to section 9.2 here. The contents of cans of diet soda have weights with a mean that is less than the mean for regular soda. All right, kind of verbose, you know, but it is what it is. The contents of cans of diet soda I'm struggling. I want to write Coke there because I know it's Coke. Have weights with a mean that is less than the mean for regular soda. All right, so like that. If I did a confidence interval for this, would you expect my confidence interval to contain 0? So if I did a confidence interval for mu sub diet minus mu sub regular, would that confidence interval contain 0? Based on our conclusion that we rejected H naught.
No.
It shouldn't. No. So, in fact, I think you ended up with negative 0.0254, and negative 0.0177. But the confidence interval should not contain 0. Not contain 0. Now, it's a little hard to judge things when you have a confidence interval based off of a one-tail test. But if it's a two-tail test, then your confidence interval should exactly match your conclusion from our p-value. But here, it's just kind of reassuring. It's nice to see that those things match. Okay. Are we good with this one?
Yep.
All right. So we're going to do one last example from this section, and that is this one here. I'll call it example C. Listed in the data are amounts of strontium-90 in millibecquerels per gram of calcium, and a simple random sample of baby teeth obtained from residents in 2 cities. We'll call them Detroit and Chicago. Assume that the 2 samples are independent, simple random samples selected from a normally distributed population. Do not assume that the standard deviations are equal. So they're telling you what button to click when you're working with Statdisk. We're going to do this at a 10% significance level. And in yellow here, I've got what we need to test. Test a claim that the mean amount of strontium-90 from City 1 residents is greater than the mean amount from City 2 residents. So, we're going to follow through with our Detroit and Chicago thing, then we'll make Detroit City 2. But let's write down some information here. So this is example C. And let's zoom out a little bit. Whoops. What happened here? That doesn't look good. Am I making you dizzy yet?
I think you inverted your screen somehow.
Yeah, I did somehow. Select camera, zoom, rotate, and mirror. No, that didn't work. Back here, rotate. That's messed up. There we go. Wonder what I did there. All right, cool. So one thing that we should look at, though, is the assumptions. Now, I'm not very good about checking the assumptions, making a habit of that, because it just kind of slows you down while you're in class. But this is something that you need to do. So let's take a look at it here and remind ourselves what those assumptions are. So we have independent samples. They gave us that. They gave us that. Both the samples are simple random samples, so we're good there. Now the sample sizes are both 12, so we don't got that going for ourselves. So the next thing we need to test is, do the samples come from a population that is normally distributed? Well, okay, we can test that. As a reminder, you can test that by clicking the data menu, then Normality Assessment. Which column of data would you like to test? Oh, well, let's test column 1. What do you think? Well, the histogram doesn't look too bad. I mean, I guess if you close one eye and then close the other eye, you can kind of fool yourself a little bit. But a little bit more telling might be the normal quantile plot. Does that look like it's a normal distribution?
No.
No. And if that wasn't enough, then let's go up here. and this is something we can understand a little bit more now than when we first encountered it. It says reject normality with a 5% significance level and reject normality with a 1% significance level. Basically what it's saying is that this data is so bad that you've proved it's not from a normal distribution at both the 5% and 1% significance level. So really the book's asking you to do a problem that you shouldn't be doing with this method, because this data is not normally distributed. All right, we're just gonna have to ignore it and soldier on with the problem. If you look at the second column of data, I think we'll see similar results with a little bit of a twist. Now it's interesting, here you reject normality at the 5% significance level, but not at the 1% significance level. So maybe somehow or another, this data isn't quite as bad. And looking at the normal quantile plot, yeah, all right, it's not quite as bad, but it's still not good. So in all honesty, they should have had an option for you to just stop here and not finish this test. Since that's not there, let's finish it up. We'll actually do the hypothesis test. So there we go. Test the claim that the mean amount of strontium-90 from city 1 residents is greater than the mean amount from city 2 residents. So that puts us at step 1. Let's see if we can't put that claim into words. And so that would be city 1 and city 2 levels. Well, which one's bigger? Or what inequality should I put in between these two?
Less than.
Let me look back here. The mean amount of strontium from city 1 residents is greater than the mean amount from city 2. So which one?
Greater than.
Thank you, greater than. And that's going to be part of the alternative hypothesis. And the null hypothesis, you're going to have mu1 is less than or equal to mu2. All right, thank you. Step 2 was at the 10% significance level. Step 3, fortunately for us, the data is already entered, because we already checked it. So that brings us to step 4. What's step 4 going to be? What do we got to do here? Suggestions? What's going to happen in step 4?
The p-value.
Excellent. We need to find the p-value. So let's going back to mean 2 independent samples. Thanks, Jalal. We're going to use data. So I'll click that one right away. And then our alternative hypothesis was which one of these 3? 1, 2, or 3? Not equal to, greater than, or less than?
Greater than?
Yes, greater than. So that'd be the third one. Our data is in column 1, and the second sample is in column 2. Do we know the population standard deviation? Should I be entering that?
No.
Nope. Nope, that would change the nature of the test. What about the unequal variances or equal variances? Should we pool our variances?
I'm gonna guess no.
You guessed right. Don't pool the variances. And that goes back to what it says here in blue. Do not assume that the standard deviations are equal. Standard deviations and variances run in the same direction, so we're not going to assume that they're equal. And I think that's pretty much it. We've got our significance level should be 0.10. Not really sure that that'll make a difference here, but it's nice to have that right anyways. Okay. So the information I needed to hear was, let's see, did I put in everything right?
I think you put less than greater than.
Oh, whew, thank you. Yeah, I did put in the wrong one because I was looking at that p-value and going, wait a minute, something's wrong. There we go. That looks a little bit better. The p-value is about 6.5%. P-value 0.065. So that brings us to step 5. How does our p-value compare to alpha?
It's less than alpha.
Yeah, it's less than alpha. Excellent. So if p is low, h naught must go reject h naught. And finally, step 6, we got to state our conclusion in words. So we have to decide, well, which form of the conclusion we're going to use. That's where you have that sheet. Might want to keep that one handy, the wording, the hypothesis. Let me erase these, then we'll start all over again with this stuff. Going back here for just a brief moment, our original claim that we're testing is that the strontium levels from city 1 were greater than the strontium levels for city 2. So let's see which one of these we're going to pick right here. And what I want you to do is I want you to privately figure out which one it is and then put that in the chat privately. Don't send it to everybody. So the original claim did not contain the condition of equality, and we did reject it. So that brings us to C. The sample data support the claim that the strontium levels from city 2, excuse me, from city 1 are greater than the strontium levels for city 2. So that would be our conclusion in words for step 6. So are we comfortable with that? All right, that's great. I'm going to stop the recording here and we'll take a